Hey guys, in this recording, what we're going to do is we are going to do a review of two important types of factoring. Of course, factoring is going to be super important when you are dealing with rational functions, when we're dealing with limits at all. You need to be sharp. You need to be right on it with factoring methods, strategies, techniques. You got to be A game, A plus. So first classic type, really I would like to focus mostly on this one right here because it'll be most relevant in the lesson that we're going to be looking at. And I think that it's a type that maybe you've forgotten how to do. This one we've been incorporating into examples already recently, and it's a little easier if you ask me, but maybe not to you, I don't know. So the first type is the difference of two squares, and the second type is the sum or difference. It's works both ways, of two cubes. Well, what's a square? What's a cube? Square is a number by or times itself. So when they had to do arithmetic back in the times of Pythagoras, they did their arithmetic using geometry because they didn't have the Arabic number system that we have today. They had like Roman numerals. Who wants to do arithmetic with Roman numerals? So when they wanted to square something like 2 by 2, think of that as dimensions. 2 by 2, well, they would literally do 2 in one direction by 2 in another direction, and they would create a shape out of that. What that made was 4 squares. They would count them up and they got 4. So your dimensions of 2 by 2 made 4 squares, the shape of a quadrilateral with right angles such that all of the sides are the same length. We call that a square. No mistake, no accident, and no coincidence. That's the name comes from there. So a square is any number times itself, similar to a cube. If we add that third dimension, not just a length and width, but a depth or a height, depending which way you look at it, 2 more in another direction. How many unit cubes will we end up with? Well, 1, 2, 3, 4, 5, 6 in the back, 7, and 8. You'd end up with 8. So a 2 by 2 by 2 would be 8. That we can call 2 squared, and that we can call 2 cubed. All right, very cute, I know. So geometry was way easier back in the day because, like I said, when they tried to do arithmetic, they didn't have our Arabic number system, which are these numbers that we use all the time. They instead had things like Roman numerals, and that would be gross. What does the difference of two squares look like? Remember, math is pretty literal. I promise, it's pretty literal. What's the difference? A difference is subtraction, 2 of something, well, 1 of thing, 2 of thing, 2 things. So the difference of two squares, well, does it mean this? Not quite. I mean, in a sense, sure, something by itself, right? 2 by 2, even the dimensions of wood or something at the, Lowe's or wherever you go, right? So something squared, something squared. What could I use? Well, if we put parentheses here in a little square, put parentheses here in a little square. What if I had something just as simple as x being squared minus 3 being squared? Well, you probably wouldn't write it like that. X being squared, do I really need those parentheses? No, that just means x times x, which is x squared. And then 3 being squared, usually it would be evaluated. What is that? 9. So something like this given to us is in a form known as expanded form. It's really also in standard form if we looked at it as a quadratic. We would really be looking at 1x squared, right? Plus 0x minus 9. But why are we going to write 0x? We just write it as the binomial x squared minus 9. That's expanded form. If we wanted something factored, remember, alphabetically, expanded comes before factoring. So if we start at expanded, we want to go into factored form. That's going to be a process. I mean, could we expand? Could we have factored and work backwards, work out and take the factored form and expand it? Yes. So I'm giving you expanded form. If I wanted you to factor it, what would you do if you knew and recognized that it was indeed the difference of two squares? Well, you would ask yourself, put on your X-ray vision glasses and just simply ask yourself, what's being squared to make x squared? Well, that one's, I hope, easy, just x. Sometimes it's too easy and you guys don't know how to answer. What's being squared to make 9? 3. Then, to set up our factored form as a shortcut method, not using AC method and grouping, which another day, what we do is we take the thing that's being squared, x, will go here and here, 3 will go here and here, and then each of these two binomials will have opposite signs. One will be plus and one will be minus. When we expand something like this, what that allows to happen is your outer and inner will be opposite. We'll have a negative 3x and a positive 3x. They'll cancel out, no linear term, no x term, no b term. And that's why we're left with the difference, because you always have a positive times a negative. So that multiplies b minus. The difference of two squares, because you'll always have something times itself and something times itself. These are known to be conjugates of each other. Conjugates, like when you conjugate a verb in your foreign language class, you keep the beginning and you change up the ending. Okay, that is how you factor the difference of two squares. You're probably going to see more elaborate examples than that, such as something like, just to squeeze one more in here, 4x squared minus 25y to the 6th. Okay, what would that look like? Well, what's being squared to create each of these expressions at the beginning and at the end? What's being squared, putting on my X-ray vision square glasses, what's being squared to make 4x squared? 2x. What's being squared to make 25y to the 6th? 5y to the 3rd. You have to know your properties of exponents really well. If it's a little blurry, I'm sorry. But if you're listening, you should be able to copy it down perfectly fine. Then you take the thing inside each of your parentheses and you just set them up inside two factors. So I'm just going to write that right here, a little sideways. So I got 2x. I have 5y cubed and 5y cubed. And then one will be a plus and one will be a minus. You really don't have much of an excuse to get any of these wrong because you can check every single one by simply using expanding. FOIL, if you will, right? So if you expand and get back what you started with, then you factored correctly. Always make sure you factored all the way, that you look for a greatest common factor first and foremost. And whenever you have a negative leading term, I highly suggest factoring out the negative before you do factoring. All right. Now let's dive into the sum and difference of two cubes. So the sum and difference of two cubes will look quite similar. It's going to be a perfect cube plus or minus. So a perfect cube, let's be funny this way, there we go, plus or minus a perfect cube. Well, what do we mean? What's a perfect cube? Something raised to the 3rd plus or minus something raised to the 3rd. We could have something as simple as, like in this example here, x raised to the 3rd plus or minus 3 raised to the 3rd. So something like x cubed plus 27, or something like x cubed minus 27. Now, I'm just going to get right to the point, right to how we factor it. I'm not deriving all of this. I do have a full lesson on both of these, the difference of two squares, as well as the sum and difference of two cubes. I will link those in the description box underneath the video, but just to get to the point and get to the rule, that's going to be in this video. So if you didn't ever really learn the proper way, I highly suggest you go back and do that, because in order to be most effective and to be most successful with examples that present themselves in so many different ways, you really need to understand the root, no pun intended, of it all, where it all comes from. Okay. Now, if you were given something like this or something like this, you need to put on your X-ray vision cubing glasses. So what is being cubed to make these things? So this or this will be given to you. You write it in one of these forms. What's being cubed plus what's being cubed, or like this, something is being cubed minus something is being cubed. What's being cubed to make x cubed? X. Well, same applies here. And what is being cubed to make 27, or what is the cube root of 27? Root, where it comes from. In that case, 3 and 3. Now, again, just a shortcut. When we factor this, we will always get a linear binomial when we factor something in this format, and a quadratic trinomial. The quadratic trinomial will be prime. Don't try to factor it. It doesn't factor. X cubed plus 3 cubed. What we're going to do, take those little cubes, put them in your pocket, those 2 3s, put them in your pocket. We're going to save them for later. They're going to turn into some fairy dust. We're going to do some magic. Those 3s are gone. What's left? Just the x plus 3. Bam. There's my linear binomial. That factor's done. This is just a strategy, a technique. As a shortcut, this is not why it works. Okay? This is just me being weird and helping you get right to the point. Okay? Now here's my fairy dust. I'm going to sprinkle the 3s. What's x times x? X squared. I'm not doing any of the signs now. What's x? That's all the fairy dust from one pocket. Times 3. That's 3x. And now I got 2 more dots of fairy dust in the other pocket. What's 3 times 3? 9. The fairy dust, well, it was glittery. And now it's all over my hands while I sprinkled it on this problem. I need to go wash my hands. What am I going to wash my hands with? Soap, of course. Soap. S-O-A-P. Same as the sign in the original problem. This one will be the opposite of that sign in the original problem. And the last one is always plus. It's always a plus sign. And that, ladies and gentlemen, is how you factor something presented to you, such as x to the third plus 27. How about this right over here? Works the same way. You do a smaller parenthesis for your linear binomial factor, a larger parenthesis for your quadratic trinomial factor. You put those 3s in your pockets, save it for the fairy dust. You got x minus 3, write that down. Sprinkle that fairy dust, x times x, x squared, x times 3, 3x, no signs yet. 3 times 3 is 9. Go wash your hands with some soap. You got too much glitter on them. S-O-A-P, same, opposite, always plus. So there you go. In a nutshell, how you factor the sum or difference of 2 cubes. Again, we could have some funky example like that one. So let's spice that up. What if it were instead 8x to the third minus 125 y to the 6th? What if we had something like that? Sorry, I didn't mean to write over that little 6 over there. Well, you have to use your X-ray vision. What is being cubed and what is being cubed? 2x. What about here? 5y squared. Okay, y squared for that right there. That was y cubed being squared. This is y squared being cubed. Keep up. Now, we're going to go right ahead and we're going to write a smaller factor. Now, because I have these y's floating in there, this is not going to use that same vocabulary as like a linear binomial, quadratic trinomial, but it's still going to be 2 terms, 3 terms, yes. So, smaller and larger. Take the 3's, put them away. What's left is 2x minus 5y squared. Sometimes this might end up being, say, the difference of 2 squares, and you could factor it even further, all right? Then 2x times 2x, 4x to the second. So that was 2x times 2x. 2x times 5y squared. That's going to be 10xy squared. 10xy squared. 5y squared times 5y squared is, oh boy, squeezing, huh? 25y to the y squared and y squared. to the 4th. And I'm just going to try to get those parentheses shut. Please be patient with this, you know, trying to squeeze it all into one notebook. Okay. Now, same, opposite, and always plus. So minus, same as that, opposite, and always plus. I'll just rewrite it over here so we can see it a bit better. So that's 2x minus 5y to the second in the first factor. And that second one is 4x to the second plus 10xy squared plus 25 y to the 4. And that's your larger 3-term factor right over there. Okay, so I hope this review helped. It is going to be quite relevant in our next examples where we are going to find limits of some sneaky rational functions. So get this all down if this was helpful and you got something out of it, put thumbs up. If, again, you hated it and it was stupid and a waste of your time, go ahead and put a thumbs down. I won't be crying about it. If you need more help with factoring, or you just, you know, want to watch, maybe you don't want to write it down, but maybe you just want to watch how to see more of a deeper understanding for either of these methods, I can link those in the description box below. Anything else you could think of, let me know. Have a great day.